Hello, good morning everybody. So, today we will continue with theories of reaction rate. So, it will be the concluding part of this section, that is theories of reaction rate. So, we were discussing this surface reactions. Surface means maybe say surface adsorbed molecules are undergoing some chemical transformation, maybe carbon monoxide. Okay. So, when it gets adsorbed onto some metal surface, then what happens to that? Maybe this kind of reactions we were discussing. Okay. So, now we were also trying to apply transition state theory on surface reactions. Okay. Now, this time we will talk about a situation when adsorbed atoms or molecules which are there on the surface, they undergo chemical reaction, that is chemical reaction on metal surface. Okay. Say there are two atoms or molecules, those are adsorbed on metal surface. So, they will tend to react with each other. So, what could be the situation? Okay. So, that is considered a surface with adsorbed atoms or molecules that react. Okay. In this case, we will leave out the details of internal coordinates of those adsorbed species, but note that their partition functions can be found using the schemes presented earlier. Okay. That is I already talked about in earlier lectures. Let us also assume that species A reacts with B to form an adsorbed product AB via an activated complex AB double dagger, okay, or AB hatch. So, schematically it is basically A star plus B star. So, these two are adsorbed onto surface. So, that is why it is A star plus B star. Okay. So, giving rise to AB, that is both adsorbed and hatch. Then what will happen to this is that this will undergo reaction to give you AB star plus star, means they combine to form AB adsorbed, and the position which was occupied say by A is now left open like this. Okay. So, so this first step is the equilibrium. Okay. So, that means you have to have one K double dagger or maybe K pound or K hatch. So, K hatch will be equal to theta AB. It is related to coverage theta A theta B, which is nothing but equal to Q AB divided by QA times QB. Okay. So, rate of change of theta AB, this rate of change of this, how can you write? You can write d dt of theta AB, okay, which is as per with transition state theory KTST times theta A theta B. Okay. So, in that case you can write your new AB, the same treatment we did earlier, K this theta A theta B. Okay. So, which will ultimately turn out to be d theta AB dt, which is equal to, you can write nu AB double dagger KB T, that is your thermal energy KB, K Boltzmann times T, divided by H nu AB, of course this activated, times Q AB primed. That means one mode is taken off. Okay. So, one mode less, that is why it is primed, divided by QA QB, okay, theta A theta B, and you can write this to be equal to like K plus theta A theta B, that is for the forward process K plus. Okay. So, basically K plus is equal to KB. You can write K plus is equal to KB T divided by H into, so because these two will get cancelled. Okay. So, QAB primed, okay, QAB primed divided by QA QB, okay, which is equal to KB T by H times QAB prime 0, okay, divided by QA QB into exponential to the power minus delta E A plus B minus AB double dagger divided by KBT. Okay. So, basically we refer here the partition function of the transition state to its electronic ground state, and we may extract the shift in energy between the two ground states by this much, delta E A plus B minus AB double dagger or AB pound. Okay. So, here we are referring this partition function of the transition state to its electronic ground state. Okay. That is why this term is here, and Q primed double dagger refer to the reaction coordinate, means one reaction means basically one mode is taken off, that is the reaction coordinate which is taken off. Okay. And that reaction coordinate along which this reaction is taking place, maybe one vibrational mode is converted to a translation. So, that is why it is primed. Okay. So, basically it is now equal to K, you refer this K0 plus e to the power minus delta E AB B minus AB double dagger divided by KBT. Okay. So, this is the expression for your K plus. Next, reverse process. Okay. Reverse process means the dissociation of AB on surface. So, then the scheme will be like this, that AB star plus giving rise to AB, okay, then this will dissociate, that is it is basically the reverse process. AB star double dagger, this gives rise to A star, basically this is this thing, A star plus B star. Okay. So, rate constant ddt of theta AB is equal to minus K minus theta AB theta star, that is the uncovered region. Okay. That is your surface. Okay. So, you can write as usual, means as in the former case, the same way you can write K minus is equal to KBT by H into QAB double dagger primed double dagger divided by QAB is equal to KBT by H into double dagger primed 0 double dagger divided by QA QB or QAB into exponential to the power minus delta E. Delta E has got the similar significance as I talked about, AB double dagger divided by KBT, which is nothing but equal to, you can write K0 minus e to the power minus whatever I wrote over here, the same quantity will be here. Okay, so this is the rate constant for the reverse process. Okay, so when we consider that both steps are under equilibrium, okay, so then what can we write? We can write that is like a steady state approximation, okay, considering both processes and an equilibrium approximation. We can write dt of theta AB, which is equal to, this is for your plus means forward process, theta A theta B minus K minus theta AB theta star, which is equal to 0 because it is equilibrium. That means rate of forward reaction and rate of backward reaction, these two will equalize. Okay, so that's why we put this to 0. We put this to 0. Okay, so what do we get? That it is equilibrium constant. We can write K equilibrium, that is equilibrium constant. If we write equilibrium constant, that is equal to K plus divided by K minus, okay, which will be equal to, from this you can if you put this, so that means K plus by K minus means basically theta AB theta star divided by theta A theta B. This way you can write, okay, and this will ultimately come out to be like QAB divided by QA QB into exponential to the power delta E AB minus AB pound or AB H delta E A plus B minus AB this divided by, this is exponential, divided by KBT. Okay. Now, what is this term? Means what is the significance of this term? Okay, means how can we relate this term with some other known quantities? Okay, so to do that, so basically from other already studied expressions, or already I told those expressions that K equilibrium can be written in terms of like exponential to the power delta S divided by KB into exponential to the power minus delta H divided by KBT. Okay. So, if we compare these two together, means if we compare this equilibrium constant as we have obtained considering this surface processes that I just talked about, and already the older expression, already we talked about this expression earlier, that equilibrium constant you can write in terms of your delta S and delta H, you can write in this way, or maybe it is a classical equilibrium constant expression, because delta G is equal to minus RT ln K equilibrium. Okay. So, basically delta G is equal to, you can write from here, delta H minus T delta S, okay, is equal to RT with a minus sign, RT ln K equilibrium. So, from this we can write ln k equilibrium is equal to delta S by R and minus delta H by RT. Okay. So, if you take exponential of both sides, then you will be getting this expression. So, now you compare these two. So, what do we get? That comparing these two, this is, you see, this is an energy term, and this is something different, you know, it is not exactly an energy term, it is a ratio of partition functions. Okay. So, if it is a ratio of partition function, and you know, already I talked about in earlier lecture, one of the earlier lectures, that this part, that is prefactor, this prefactor term has got a connection with entropic term, and this has got a connection with an energetic term. So, therefore, we compare this part with this one and this part with this one. Okay. So, that means this entropy of activation term, okay, or maybe entropic term, is basically coming from your ratio of your partition functions, and this is coming from this energetic term. So, you see, if we look into the diagrammatic representation, then this is your potential well for A star plus B star. Okay. This is your activated complex, or that is your transition state, that is AB H star star. So, that is, these are adsorbed and they form, these two, adsorbed A and adsorbed B, these two will form an activated complex. So, that's why it is represented AB star, a double dagger star star, and then it will come down to here, giving rise to AB star plus star. Star means one, maybe one position, one chair is made vacant. Okay. So, what is this? This is the energy difference between this activated state and the adsorbed AB star, that is why adsorbed AB star. Okay. And what is this? This is the energy difference between your activated A, activated B, and this complex, I mean activate, I mean adsorbed A, adsorbed B with your this activated complex, adsorbed activated complex. Okay. So, this is your adsorbed activated complex, this is your adsorbed A and adsorbed B, this is your adsorbed AB, and one site is kept vacant. Okay. So, this is the energy difference, that is why it is written, this gap is your delta E A plus B minus AB pound or double dagger, and this is your delta H of reaction, that is your energy of this state and difference in energy of this state and this state. Okay. So, that is why, you know, you see that if this is a reaction between A star plus B star giving rise to AB star plus star through this activated state or through this transition state, then your equilibrium constant can be expressed in this way, where this is a ratio of, you know, ratio of the partition functions, and this is your energy difference term, exponential of energy difference term. Okay. And therefore, this energy difference term can directly be related to the heat of reaction, and this ratio term can directly be related to your entropic term. Okay. So, that is why equilibrium constant can alone be determined from the initial and final state partition functions. Okay. So, initial state and final state and initial state partition functions. Now, we will move on to desorption. Okay. Once this reaction is complete, okay, that is formation of AB star is complete, then it should dissolve from the surface. Okay. So, this you know, prescription is AB star in equilibrium with AB star double dagger or AB star H. So, AB, it is a desorption process. desorption process. Okay, AB star equilibrium, AB pound, then AB star pound or star hatch giving rise to AB, plus the site is vacant now, has now become vacant. Okay, so this is purely a desorption process. Okay, so now what is theta AB hatch, which is equal to NAB divided by M. The significance of N and M is already told, so that is it is this by that. Then QAB divided by QAB theta AB. Okay. From this it can be written that K hatch or K double dagger theta AB. So, in some books you will be finding means in place of this hatch is symbol like this, double dagger. Okay, so that is why we may call this as hatch or maybe double dagger, or maybe sometimes it is called as pound symbol. Okay, so K double dagger is equal to this by theta AB, which is equal to QAB divided by QAB. Okay. So, rate of desorption or rate of the process is nothing but minus d theta AB. So, it is decreasing, that is why it is minus sign dt, which is equal to K TST into theta AB. So, this K from TST has always to be included, which is equal to nu AB, this K double dagger theta AB. Okay. So, that means this is your nu NAB double dagger divided by M, and you can approximate this to KBT, Boltzmann constant, temperature divided by H times Q prime AB divided by QAB into theta AB. Okay, which is equal to KBT divided by H into same treatment as I did just earlier from now, divided by QAB exponential to the power minus delta E KBT, sorry KBT theta AB. Okay. So, that means your nu into e to the power minus EA by KBT into theta AB. So, this is the net rate expression. So, this is your energy of activation, I mean exponential activation energy divided by KB into T. Okay. So, the adsorbed species may be bound rather strongly and considered immobile at the bottom of the vibrational ladder. The transition state can have several possibilities. Okay. So, once the species it is adsorbed and bound rather strongly, and when it is considered immobile, that means it is at the bottom of the vibrational ladder. Okay. That means if we have this vibrational ladder like this, this is a ladder. So, this is the bottom of the ladder. So, here motion is less, that is why it is more or less less mobile or immobile. The transition state can have several possibilities. For example, a precursor that is highly mobile in 2D Thus, depending on the magnitudes of partition functions of rotation and translational motions, the pre-exponential factor for desorption may become significantly large than the standard value kT by h, which is of the order of 10 to the power 13 per second. Okay. So, that means depending on the magnitude of the partition functions of the rotation and translational motions, the pre-exponential factor for the desorption process may be large. Okay. And most of the pre-exponential factors for CO desorption can be rationalized in terms of loose transition state. Okay. So, let us have various systems. That system with different system, that is as if your here it is carbon monoxide is adsorbed onto various planes of different metals, that is one is 111 plane, or maybe 100 or maybe 001, like that. And so, the system is this, prefactors per second is this, and energy of activation is kilojoule per mole, this much of kilojoule per mole. Okay. So, so in the first case you see that when carbon monoxide is adsorbed onto nickel 111 plane, okay, crystal plane. So, it has got the pre-exponential prefactor of 10 to the power 15, it is high, and energy of activation is 130. For nickel 111, it is 10 to the power 17 and 155. Then there are various options you can have. Then carbon monoxide nickel 110, it is, you see that 10 to the power 14 and it is 130. Okay. And then it is carbon monoxide Cu 100, it is 10 to the power 14 and 67. Okay. Carbon monoxide ruthenium, okay, 10 to the power 16 and 160. Carbon monoxide rhodium 111, it is 10 to the power 14 134. Okay. So, these are the various values of prefactors. Okay. Now, if you look into this, that here this is your adsorbed state, okay, this is your transition state, this is your dissolved state, and these are the pre-exponential factor. You can see that if the adsorbed state is like this, that is, it is adsorbed onto the surface, then it can have two options. One is mobile, another is immobile. When it is mobile, then it can move around in two-dimensional surface on the metal, maybe carbon monoxide or maybe maybe nickel or maybe copper. It depends, means whether if it is mobile, then it can have two-dimensional motion, because third dimension, this one, third motion, this motion is not possible because this side it is bonded. Or it may be immobile, that is, it does not have any option to move around, maybe x or y direction. Okay. And the dissolved state for both of these is like this, that is, distance is increased a little bit, and the pre-exponential factor comes out to be, you see that it is 10 to the power 15 and it is 10 to the power 13. Okay. So, so basically basically you see that for immobile case, it is the value is less, prefactor is less. Okay. But for if it is mobile, then prefactor is high. What about this, say, diatomic system? Okay. So, it can have a mobility, or it may not have mobility. So, if it is mobile, if its adsorbed state is, transition state is this is the adsorbed state, then it will have motion like this motion, it is a rotational motion, or maybe a translational motion. Okay. So, basically it is a mobile situation, and for immobile, you see, it does not have any option to either rotate or maybe translate in this direction. So, it is immobile, and your dissolved state, this is the adsorbed state, or this one is the adsorbed state. So desorbed state means when it leaves the surface, then it is like this. And for your mobile case, it is 10 to the power 14 to 10 to the power 16, it is high, and for immobile case it is 10 to the power 13. You see, for both cases, when it is atom or maybe molecule, you see the immobile case your pre-exponential factors are close, and of course this is lower than corresponding mobile case. Okay, and activation energy is delta E plus kBT. Next, so through this discussion, it is clear that that we have been able to understand, we have been trying to understand this surface reactions and application of transition state to surface reaction. And in that case, what we have done is we have applied the prescriptions of statistical thermodynamics. We have derived expression for the adsorption, reaction and desorption of molecules or atoms on and from the surface. The rate constants can in each case be expressed as the ratio between the partition functions of the transition state and reactants. Okay. So we have expressed the rate constant in terms of the partition functions of the transition state and the reactant states. Okay. And here we have tried to utilize the statistical thermodynamical prescriptions to find the partition function which we have applied, which we have employed in finding out the rate constant of the process. Okay. So we, in this particular lecture, what we have particular part of the lecture, because next we will move on to next we will move on to diffusion controlled reaction. Before that, what we did this in this part, that we have invoked the idea of surface reaction. It is not simply the adsorption and desorption process. Once these molecules get adsorbed onto metal or onto some surface, then there is every possibility of reaction. Why every possibility of reaction? Because at par with this collision theory, that when there is a collision, then there is a possibility of reaction. That means they must come in proximity to each other. Okay, like they will come close to each other, and then there will be a reaction. Okay, and in this case, these are gas phase molecules. When they collide, they are truly gas phase molecules. But when the question of a metal surface comes into action, then these two molecules are now in a state of adsorption like this. Okay, so these two are adsorbed onto the metal surface. Okay, say this is your metal surface, so these two are adsorbed. Okay, so these two may have motions like this, maybe like this, or maybe like this, or something like this. Okay, so that means they may have mobility or they may not have mobility. Okay, but the thing is that when they are adsorbed onto the same metal surface, they have the option to come close to each other. That means an option of reaction on surface, that is a reaction of adsorbed molecules on metal surface, and that we have tried to implement, that is reaction between surface species, and we have got some expression of the overall rate of the process. And when there is adsorption, when there is forward process, there is equal probability. There is some probability of the back reaction to occur. Therefore, we have also included that possibility. Okay, so and we have got some expression for rate constant for the dissociation of AB on surface as well, because the forward reaction was the formation of AB. The back reaction will be dissociation of AB into A and B. Okay, and we have applied the concept of equilibrium, because at equilibrium forward and backward reaction both are forward and backward reaction rates are identical. Therefore, we employed that and we got the expression for the equilibrium constant in terms of the energetic an energetic term and you know partition function, and ultimately we compared this with expression for equilibrium constant, and we come out with the conclusion that this QAB divided by QA and QB, it is your entropic term. So, this pre-exponential term, okay, this pre-exponential term is related to your entropic term, and your exponential term is related to energetic term and has got some relation with your energy of activation. And then we have employed desorption process, that once this molecule I mean AB is formed, this may undergo desorption, that is leaving the metal surface. Okay. So, desorption process. So, from that we also have got the rate expression for the desorption process. Okay. So, and depending on whether it is highly mobile or less mobile, whether whether it is whether the magnitude of the partition functions, that is rotation and translation, these are very high or low, the pre-exponential factor for desorption may become significantly high. Okay. So, pre-exponential factor significantly high means there is a high probability of desorption rate, that is it will contribute considerably. Okay. And we have got some typical values of the pre-exponential factor, pre-factor, and we have given also the diagrammatic representation of various adsorbed states for atoms and also for molecules, and we have also tried to rationalize, okay, why this pre-exponential term is high, because pre-exponential term high means it is related to entropy, and since for the mobile case, although it is adsorbed onto the metal surface, okay, this metal surface, but what is happening that this has this mobility option in this direction or maybe in this direction. So, if it has got the mobility option, then your entropic term will contribute significantly. Okay. So, entropic term when entropic term contributes significantly means it will surely give you some higher value. That is why this, you see that pre-exponential factor for the mobile case, mobile transition state case, it is you see about 100 times more, okay, than your this pre-exponential factor, where this is immobilized, this adsorbed stuff is immobilized. So, this motion or maybe some rotational motion for molecules, it is not possible. Therefore, it is associated with a reduction in entropy. So, reduction in entropy means for sure your pre-exponential factor will be less. The same can be concluded, means we can have the similar conclusion and similar explanation when we consider adsorption of molecules onto the surface. And in that case, you see that if it is a mobile situation, then your pre-exponential factor, this pre-exponential factor is quite high, about 10 to the power 14 to 10 to the power 16. Now, why it is still about how much, about 10 to the power 3 times more, 10 to 10 to the power 3 times, 10 to 1000 times more, depending on which molecule is adsorbed. Okay. That means when entropic term contributes considerably, then it contributes towards a high means it leads to a high pre-exponential factor. Okay. That means throughout this discussion of the surface reaction and application of transition state theory, okay, we have tried to apply the statistical thermodynamical expression to derive the relation that relates the adsorption process or reaction or desorption process with with partition function. Okay. Next will be we will move on to another specific reaction, because if we go to the very first slide that we have just completed this theories of reaction rate. Okay, we have explained gas phase reaction, we have tried to explain the solution phase reaction, and now we have explained, we have discussed the surface reactions. Okay. So now we will move on to another topic, that is kinetics of some specific reactions, specific type reaction. Okay. That is your diffusion controlled reaction. What is that diffusion controlled reaction? Consider a reaction, say a simple reaction, say hydrolysis of ester, acid catalyzed hydrolysis of ester to give you acid, as acid means the organic acid, and your alcohol. Okay. So that is your R C O O R, okay, H plus, giving rise to R C O O H plus R primed. Okay. So this is acid catalyzed hydrolysis of ester. Okay. So if you measure the reaction, I mean rate of reaction, then you will be finding that it takes time. It is not very fast, it happens slowly. The concentration of this RCO, that is acid concentration, slowly rises with time. Okay. So it does not happen all on a sudden. It does not happen like an explosion. Okay. So it takes time. But suppose if we have a situation that we have got reactant A and reactant B, if they come close to each other, it will form AB immediately, means it does not take any time. Okay. That means we can say that possibly, means we can assume that maybe this reaction barrier is not there, possibly reaction barrier is not there. Reaction barrier means this one, this is a reactant, this is your product, and say this is your forward reaction barrier or activation barrier is probably not there. If the activation barrier is not there probably, then these two will immediately combine to produce B. That is, if you have the option to bring A and B close to each other, okay, then with one collision, maybe if we consider that collision theory is the theory by which we can explain everything, or if we just think of collision, then in a single collision it will make a bond. Like if you think of this H plus and OH minus reaction, okay, that is to produce water, plus OH minus, acid base reaction. Okay, to produce water. So it's a very fast reaction. Now the question is that what type of reaction is this? The thing is that this very fast reaction are generally its rate is diffusion limited. it says that its rate is diffusion limited. Diffusion limited means it is of the order of nanosecond -9 or -10 seconds. It's 10 or its rate is very high, 10 to the power 9, 10 to the power 10 or 10 to the power 11 per second. So it's a truly if it is a truly diffusion controlled reaction, then suppose you have got one H plus over here and one OH minus over here, okay, and then what you do, you mix them together, but there is a separation, physical separation, like they are at some distance. Then what will happen? Now even if these two are present in same pot, same container, they may not form water, okay, at such a separation. They will not form water at such a separation. They have to come, okay. So coming or coming close to each other, this process, okay, so they have to swim, okay, and they will move towards each other, okay. So if if the viscosity, say, of this solvent is, if it is very high, then flow of this OH minus or movement of OH minus from here to this position, or maybe H plus from here to this position, will really be affected, that is, will become slowed down, okay, will become slowed down. So that means even if this reaction is very fast, but it will take time, and that rate is determined by the viscosity, or in turn it will be determined by how easily these two ions will diffuse to each other, okay. So it is, so rate is called diffusion limited rate, okay. So schematically it is shown like this: A plus B plus B giving rise to A, B, which is called an encounter complex or encounter of two molecules. This is designated by this. So it is diffusion, okay, and then this will form your product, okay. This is your reaction, okay. So this is called your encounter of AB, okay. So what is happening actually? Consider molecules A diffusing through the solution, okay, and it is encountering, say, a stationary B molecule, okay. So it is like your collision between two gas molecules, okay. So that means since the molecules are having, or the atoms are having some definitive volume, therefore it will have a sphere of influence, and when this atom is moving, this sphere of influence is also moving. So when a second atom or molecule is within this sphere of influence, okay, so what will happen? That is the sphere. Then there will be a collision. That means this diameter of this sphere will be or the radius of this sphere will be sum of the individual radii, okay. So the flux of A through the area AS, suppose you have got this atom, and say this is AS. Why AS? Because AS is basically your RA plus B, RAB. So AS is this pi RAB whole square. So flux through the area AS means, through this area AS means, if there is any B molecule within this area, then there will be collision, there will be encounter complex, and that will lead to the product formation, okay. So flux of A through the area AS is given by dNA dt, is equal to minus of dAs dCA dt. So where is this is your diffusion constant, diffusion coefficient, okay. So for for spherical particles, D can be obtained in terms of Einstein-Stokes equation. Okay, it is a famous equation. It was named after Einstein and Stokes because these two scientists worked on this. Okay, so your diffusion constant is R into T divided by 6 L pi R eta. Okay, so eta is our coefficient of viscosity. Okay, and from diffusion law, second order rate constant of diffusion controlled reaction can be derived that K is equal to 4 pi L dA plus dB times RAB. Okay, so this is a special type of reaction, and I will talk more about this diffusion controlled reaction maybe in the next lecture. Okay, but the thing is that this reaction is of great importance, since when there is no barrier, there could be barrier and there could be barrierless process. Okay, so when there is no barrier means no activated rate process, then simply this reaction will be very much dependent on how easily these reacting species are coming close to each other, how easily, and that easiness is very much dependent on several factors like temperature. Temperature will increase the average motion, because thermal energy when it is put onto the system, so their relative mobility will be more. Then of course on the viscosity of the medium, if viscosity is more, then the reaction rate, the diffusion process will be slowed down. Okay, diffusion process will be slowed down. So these factors are to be taken into consideration with great importance. Okay, so like I gave you the example of H plus and OH minus combination. So its rate is very fast, and you cannot simply measure this reaction rate by what we do for conventional kinetic studies, because it is very fast. The moment you will mix H plus with OH minus, all on a sudden, means the moment these H plus and OH minus will come close to each other, it will just make water. So therefore this particular type of reaction where the rate is very fast, because it doesn't there is no barrier, apparently there is no barrier. So if there is no barrier, only barrier is the diffusion barrier, and diffusion is basically you have got, say, diffusion can be regarded as, say, you have got several holes within say liquid, and say your molecule or your entity that has to be transported from here to here. What do you require? That you have to jump, means you have to put this over here, therefore this position will be vacant and this position will be occupied. Again this will jump from here. Okay, so this way. Okay, so that means if there is one molecule already occupied, then what will happen? That it has to leave this space and it has to remove this, means the already occupied molecule. So that means that will require some energy. Okay, and so that means it is the diffusion barrier that is responsible for slowing down the process. So diffusion is ultimately a very important and determining factor for this very, very fast reaction. These are called fast reactions. I will come to this fast reaction, means how these rates can be measured, that is for the first reaction, which is called, the method is called stopped flow technique. So that I will talk about maybe towards the end of this the series of lectures, and where I will also discuss the techniques by which you can measure reaction rate. Techniques means maybe analytical, maybe spectrophotometric, maybe other methods like stop flow, maybe plug flow, maybe temperature jump method. There are many methods, so that we will discuss. Okay, so we have just started this specific type of reaction, that is your diffusion controlled reaction. Okay, so in the next lecture we will continue to this diffusion controlled reaction, and then we will move on to the one important factor, that is you know what happens when salt is added onto chemical you know chemical reaction, that is if the reaction is carried out in a medium containing salt, added salt from outside, then what is going to happen? Does it really affect the overall rate of the reaction or not, and what are the factors, means what are the conditions that you will be getting some influence of salt, added salt? That we will discuss in the next lecture. Okay, so till then, have nice time. Thank you.